giant glowing spheres of plasma. That's what stars are, and our Sun is just one of the billions in the Milky Way galaxy. The cosmos is also home to billions of galaxies, and each one houses billions of stars. So sit back, grab something to drink, and join me as you enter a journey through the life cycle of a star. Stars have different luminosities and lifespans depending on their individual masses. It is their mass that determines their destiny. They may evolve as a white dwarf, neutron star, supernova, or even a black hole at the end. However, all stars, no matter how massive they are, go through the same life cycle, beginning as a cloud of gas and ending as a stellar remnant. Even while it may look like there is nothing there, there are actually clouds of gas and particles dispersed across space. This is the interstellar medium, where gas and dust are spread. Hydrogen atoms make up the vast majority of the gas. At the same time, traces of heavier elements can also be observed across the void of space. A large cloud of dust and gas, known as a nebula, can form out of this interstellar medium. During the shrinkage and warming of a concentrated area in a nebula, this is where all stars, including our own Sun, get their start. This enormous, slowly rotating cloud is made up of hydrogen and helium. Certain elements, like hydrogen, glow so brightly that it allows astronomers to spot them in the night sky. For an example of a star in this stage of its life, look no farther than the Orion Cloud Complex in the Orion system. The cloud collapses inward due to its own gravity. As it gets smaller, it spins faster and faster, eventually producing a disk with the outer sections and a roughly spherical clump in the center. When a great deal of gas and dust clump together, they will become hotter and denser, eventually forming a ball-shaped protostar. If the temperature reaches 1.8 million degrees Fahrenheit or 1 million degrees Celsius, nuclear fusion takes place, igniting the star. Unfortunately, not all of the protostars reach their final destination. If the protostar does not accumulate enough mass, a brown dwarf will form. They are neither small enough to be considered a planet, nor large enough to be called true stars. These unfortunate little fellas are substellar objects with masses less than a tenth of the Sun's, which are not enough to keep hydrogen fusion processes in their cores. For millions of years, they just continue to shine faintly and appear to be stars even if they aren't, until they cool down and fade away. But once a protostar passes the requirement of having enough mass, hydrogen fusion begins. The result is a T-Tauri variable star. This baby star creates strong winds that push the gas and molecules around it away. Because of this, its luminosity changes over time, allowing scientists to detect its formation. The star will continue to collapse for another 10 million years or more until it is massive enough to combine hydrogen into helium. Then it will enter the main sequence phase, the same one our own Sun is in. Helium is being created from fusing hydrogen in its core during this stage. This is also where the star should enjoy the most of its existence, since it accounts for 90% of its lifespan. The outward push of the gas pressure inside the core is just enough to counteract the inward pull of gravity, creating a stable state called hydrostatic equilibrium. This is what makes stars spherical in shape, providing a solid form. From here, though, a star's fate is entirely dependent on its size and mass. The more massive a star is, the faster it burns through its hydrogen fuel and the shorter time it spends on the main sequence. Low, medium, and high mass stars all have different outcomes, and we'll go over them one by one. Let's begin with those that have low masses. Lower mass stars' fusion reactions are slower, thus they spend more time on the main sequence. During this phase, they're identified as red dwarfs, the faintest but most common stars in our universe. These little buddies are thought to live for hundreds of billions of years, if not trillions, and it turns out that not a single red dwarf in the entire universe is old enough to have diverged from the main sequence. They just continue to give out a faint crimson glow from their bodies. Unlike red dwarfs, medium mass stars like our Sun eventually leave the main sequence. These stars have masses up to 8 times or less that of our Sun. Once their core hydrogen is completely fused into helium, gravity will prevail. It undergoes a rapid transformation, where gravity smashes everything down into the star's core. It then rapidly heats it up, and nuclear radiation can no longer be able to prevent this. When this happens, the star's outer layers expand immensely and can grow up to 100 to 1,000 times the size of the Sun, causing the medium star to become a red giant. The star's power is dispersed over a wider area as it expands. As a result, the star loses heat and cools to a level just above half that of the Sun. This shift in color towards the red end of the spectrum is what makes a star a red giant. Red giants then become white dwarfs. When the outer gas layers radiate away as planetary nebulae, what's left is just the core. These relics of long-dead stars are incredibly dense. On Earth, a teaspoon of their composition would be as heavy as an elephant, weighing about 5.5 tons. A white dwarf will continually drop its temperature to the point that it becomes a black dwarf. If they existed now, such objects would be difficult to spot because they give off neither heat nor light. Black dwarfs also take quadrillions of years to evolve, as the universe is still relatively young. With an age of 13.8 billion years, no black dwarfs are known yet. If you're wondering about supernovas, neutron stars, and black holes, this is where the massive stars come in. These stars have more than 8 times the Sun's mass. During their main sequence, they are blue and hot, shining 1,000 to 1 million times that of the Sun. And upon leaving the phase, the massive star evolves into a supergiant. The best example is Rigel, the brightest star in the constellation Orion, and roughly 20 to 25 times as massive as the Sun. The lifespan of a supergiant star is the shortest of any type of star. Its temperature will keep on rising until it is high enough and carbon can be fused into more complex compounds. Carbon, neon, oxygen, and silicon are all heavier elements that will be burned up by the star in this order. As it continues to burn, it will eventually reach its iron core, which will trigger a far more violent but beautiful death. Once supergiants exhaust their fuel, they can explode as a supernova. For these stars, a spectacular exit is preferable to a quiet demise. When they explode, everything they have is hurled into space at rates of between 9,000 and 25,000 miles per second. With that kind of speed, they sure are in a hurry. But this doesn't mean that the star's remnants are entirely lost. Some of it joins the interstellar medium again to create new stars, while its core can either be left behind in the form of a black hole or a neutron star. Both of these stellar remnants are extremely destructive, but breathtaking in their aesthetic qualities. In the moments before its explosion, a star must have between 8 and 20 times the Sun's mass to collapse into a neutron star. It's not easy to track them down, and even if you do, they seem to be shrouded in mystery. Even though they are only roughly the size of a city, these things should not be taken lightly. A neutron star can have twice the Sun's mass, yet only the size of a city like Los Angeles. So you can imagine how dense they are. It's estimated to be 1 billion tons for a teaspoon of a neutron star. Because of this extreme density, their surface packs a powerful gravitational pull. If stars are 20 times more massive than our Sun, the supernova can collapse into a black hole. Its gravity is so strong where in space around it is literally sucked into them, and even light cannot escape. That much gravity requires squeezing matter into a tiny space. To give you an idea of how small a black hole needs to be, imagine squeezing the Earth until it's the size of a pea. Nothing can escape a black hole's embrace once it reaches its event horizon. Thus, this mysterious and terrifying force may both slow down time and rip you apart. If something crosses its path, it will never be seen again. They're like the bully of space, only that we could need their help to survive. Due to their ability to shatter matter into elementary particles, some scientists have credited black holes as a key player in the process of element creation, the elements of which our planet is made. In galaxies, stars serve as the structural cornerstones. A galaxy's past, present, and future can be revealed from the stars by studying their ages, distributions, and elemental makeups. Undoubtedly, the stars also have been used by mankind as a navigational aid on Earth. They would shine brightly at night, illuminating the sky for anyone who needed it. From being a giant gas cloud to becoming a protostar, entering the T-Tauri stage, then into the main sequence, expanding, fusing, and finally into a peaceful or spectacular end, they definitely go through a lot on their journey. But no matter how big or small, old or young, stars are undeniably some of the most stunning and lyrical objects in the universe. Therefore, the next time you look up at the night sky, keep in mind the grandeur of how a star goes through its life cycle. While we may be unable to create stars here on Earth, we can certainly enjoy a lot of them in a beautiful night sky. Did you learn anything new about stars from the video? Share your thoughts in the comment section below. Don't forget to hit the subscribe button and leave a like. Thanks for watching.